Today we're going to talk about linear dependence and linear independence. But before we do so, let's have a review of linear combinations and span. Let's start with an example. Let's let V be R3, that is three-dimensional space, and we want to choose the following three vectors, capital A, capital B, and capital C. We wish to define a plane going through these 3 points. The intuition here is that we can start at a vector A, and then we can move in 2 directions, which we'll call U and V. One direction will be the vector that starts at A and ends at B. The other one will be the vector that starts at A and ends at C. Putting all of this together, we then find our set W. This will be the plane going through these 3 points. You can see with the graphic here at the bottom of the slide, the W just corresponds to this light blue shaded region. Here you'll see that you have a region that goes through the vectors A, B, and C. Of course, this region does extend infinitely far all throughout 3 space. Once we have our set W, we see that this is a plane through the origin precisely when we can pick one of the vectors, let's say A, to be the origin. And in fact, this is an example of a vector space. The graphic here at the bottom of the screen shows a few examples. For example, W might be the green shaded region, or it might be the blue shaded region, or perhaps even the red shaded region. Each one of these is a plane going through the origin. This means that actually in three-dimensional space, R3, there are infinitely many such vector spaces. Let's recap all of this by kind of thinking of this in 2 different ways. First, to get better intuition, let's take a look at R2, that is the real plane. We've seen that every line through the origin is a subspace of V. Well, one way we can write a line is to think of this as the set of points x and y such that ax plus by equals 0. Another way to think of the line is the set of points that are moving in a direction. That direction is where we're calling our vector u, negative b, a, and we can either move all the way to the right or we can move all the way to the left along this line. The motion is where we're calling our scalar s. This can be any real number. Similarly, let's take a look at R3, that is 3 space. We've seen that every plane through the origin is a subspace of V. Well, one way we can write a plane as it's the set of points x, y, z such that ax plus by plus cz equals 0. Another way to think of this is the set of points now that are moving in perhaps one of 2 directions, either in the u direction or in the v direction. Here, saying that we can move in some combination of those 2 is writing s times the vector u plus t times the vector v, where s and t are scalars, they're just real numbers. We can put all of this together now to find a definition. Let's let V be a vector space over a field F, and let's choose a finite subset that we'll denote as S. This will consist of vectors u1, u2 through u sub n. We call a vector a linear combination of vectors from S if we can find scalars a1, a2 through a sub n such that our vector v is a sub 1 times the vector u1 plus a sub 2 times the vector u2 plus a sub n times the vector u sub n. The scalars a sub I we'll call coefficients. If we take all of these linear combinations and put them together into one big collection, which we'll call W, it turns out that this is a subspace of V. Given our finite set S, we'll call this set W the span of S, or we'll say that S generates W. If S is the empty set, that is, it contains no elements, we define the span of S to be the trivial subspace. Going back to the examples from before, we can rethink of these in terms of span. Going back to the real plane, we see that every line through the origin is actually the span of some vector u, namely the direction we could pick here to be negative b, Similarly, in three-dimensional space, we can see that every plane through the origin is the span of two vectors, u and v. We can think of the span now as saying that we can move in two different directions in our plane, the u direction and the v direction. We also found that there was a nice application of all of this that'll be very useful as we move throughout the course. Let's say that we have a system of m equations and n unknowns. The unknowns here now are the variables x1, x2 through x sub n. We'd just like to know, when does this system have at least one solution, x1, x2 through xn? To answer this, we're going to slightly rewrite things by using a linear combination of vectors. Let's think of the coefficients a sub 1, 1, a sub 1, 2, and so forth as just being entries in a series of vectors that you can see here on your screen. By looking at the first row, the second row, and so forth, we actually can recover the various equations at the top of the screen. So this means that now we're going to rewrite our system of m equations as just a linear combination of m-dimensional vectors. We'll view this collection of vectors, which we'll call S, as a finite set, and we'll view a vector b as just the coefficients corresponding to the right-hand side of these equations. So the result states that for this system of m equations and n unknowns, there is a solution that we're calling a vector x, corresponding to coordinates x1, x2 through xn. Such a solution exists if and only if the right-hand side, our vector b, is contained in the span of S. So for the next few lectures, we're going to spend more time trying our best to determine a bit more about the subspace corresponding to the span of a given subset. To this end, let's maybe talk about a motivating example to get a better idea of what definitions we'd like to focus on next. Let's say that S and T are two subsets of a vector space V. When does it perhaps happen that the span of S is equal to the span of T? For example, if T is contained in S, can we still have the equality that the span of S is equal to the span of T? Well, as a specific example, let's let V be three-dimensional space, R3, and let's consider two subsets, S and T, in terms of the four vectors that you see here on your screen. T will consist of just three vectors, u1, u2, and u4, whereas S will consist of all four that you see. We see here that T is contained in S, so we expect that the span of T is contained in the span of S. The intuition here is that T really consists of just three directions that we can move in, whereas S consists of four directions that we can move in. So it should be clear that if you have a space in which you can move in three directions, that'll be contained inside of a space where we have more degrees of freedom, that we have more directions we can move in. Hence, the span of T is contained in the span of S. But we note something else. The vector u sub 3 is a linear combination of u sub 1, u sub 2, and u sub 4. That is, u sub 3 is twice u1 minus 3 u2 plus 0 u4, which actually means one of those four directions must be contained inside of the span of T. So we really don't have four directions, that is, the vectors in S. We really only have three directions. So we would say here that the span of T is equal to the span of S. As we just mentioned, u sub 3 is a linear combination of the other three vectors, u sub 1, u sub 2, and u sub 4. But could we have done the same thing with the vector u sub 4? That is, how do we know that u sub 4 is not in the span of the first three, u sub 1, u sub 2, and u sub 3? Well, if this were the case, then we should be able to write u sub 4 as a linear combination of u1, u2, and u3. That is, expanding all of this out, we would expect to find scalars a1, a2, and a3, where here we have a sum of vectors, and by looking at the first, second, and third rows, we would find a system of 3 equations and 3 unknowns. Later in the course, we'll discuss the idea of performing row reduction so that we can actually have a method of solving this system of equations. But for the moment, we'll ignore this and just come back to this later. But we'll say that we cannot find a solution. That is, there are no a1, a2, and a3, such that this system of 3 equations and 3 unknowns holds. Which means that u sub 4 is not a linear combination of u1, u2, and u3. So the vector u sub 4 is not in the span corresponding to the first 3 vectors. We're going to use this example now to try to introduce the concept of linearly independent sets and linearly dependent sets. Let's recall some definitions we've introduced up to this point. Let V be a vector space and choose a finite subset S. We call vectors V linear combination of vectors from S if we can find scalars a1, a2 through a sub n such that V equals a sub 1 times the vector u1 plus a sub 2 times the vector u2 plus a sub n times the vector u sub n. We can place all such linear combinations together into one collection, and we call this collection the span of S. This is a subspace of our vector space V. If S has no elements, that is, S is the empty set, we call the span the trivial subspace. We say that S is a linearly dependent set if there exist scalars a1, a2 through a sub n, not all 0, such that the sum a1 u1 plus a2 u2 plus an u sub n is equal to the 0 vector. Such an equation is called a non-trivial expression of the 0 vector. If we cannot find scalars, not all 0, such that this is the case, then we say that S is a linearly independent set. Let's try to work through an example of this to get a better idea of what this says. Let's work inside a 4-dimensional space, that is R4, and let's consider the set S that consists of the 4 vectors you see on your screen. We'd like to know, is S a linearly independent set? Well, to answer this question, we need to find a non-trivial expression of the 0 vector. That is, we're looking for scalars a sub 1, a sub 2, a sub 3, and a sub 4, such that a1 u1 plus a2 u2 plus a3 u3 plus a4 u4 is equal to the 0 vector. Expressing this sum here by looking at the first row, second row, third row, and fourth row, we actually find a system of 4 equations and 4 unknowns. We can do some work and actually find the set of all solutions. Again, later on in the course, we'll discuss the concept of row reduction to turn this into an algorithm, but for now, let's just say that by some method, we can find the solutions, and we realize that a1, a2, a3, and a4 all correspond to a scalar multiple of some vector. Here, S is any real number that you like. For example, if we were to choose S is equal to 2, then we would find a solution a sub 1 equals 4, a sub 2 equals negative 3, a sub 3 equals 2, and a sub 4 equals 0. Now this is not the only solution, but this is a non-zero solution. Not all 4 elements are 0. Notice that a sub 4 is 0, so we could have one of them as 0, but the important thing here is that not all 4 of these are 0. Moving back to the reason why we were looking for this solution here, we see now that we have a non-trivial expression of the 0 vector. This actually gives us the proof that the set S is a linearly dependent set. It is not linearly independent. More generally, how might we determine that a set S is a linearly dependent set? Well, we have a result here that corresponds exactly to the example that we discussed earlier, our motivating example. Let's say that T is a subset of a vector space V, and we know by some method already that T is a linearly independent set. Let's choose a vector, lowercase v, that is not in our set T, and let's let capital S be T union this new vector, lowercase v. Simply put, we've taken our set T and we've added a vector, lowercase v, that does not already appear in this set T. This new set we're going to call our set S. The statement is that this vector, lowercase v, is in the span of T if and only if S is a linearly dependent set. We'll try to explain the proof of this. Notice that we're using the phrase if and only if, which is a biconditional. So this means that we have two directions we must show. First, let's assume that our vector, lowercase v, is in the span of T. We'll show that our set S is a linearly dependent set. Well, if v is in the span of T, then this means that v can be expressed as a linear combination of the vectors from T. Now, taking this vector v and moving over to one side, we then find the expression a1 times u1 plus a2 times u2 plus an times un minus v is equal to 0, the 0 vector. But instead of saying minus v, we'll say plus a sub n plus 1 times v, where a sub n plus 1 is equal to negative 1. But now this last coefficient, a sub n plus 1, is not 0. So here we have a linear combination of the vectors from S, where not all of the coefficients are 0. By definition, our set S is a linearly dependent set. Let's now prove the opposite direction. Conversely, assume that our set S, remember this takes the elements from T and we're adding in one more vector, namely the lowercase v. Let's assume that this set S is a linearly dependent set. We'll prove that the vector v is indeed in the span of T. Since S is linearly dependent, we can find a non-trivial expression for the 0 vector. Let's say a1 times u1 plus a2 times u2 plus a sub n plus 1 times v is equal to the 0 vector, where not all of these scalars are 0. We're going to consider two cases. First case is when the last coefficient, a sub n plus 1, is 0. Then this means that we have a sum a1 times the vector u1 plus a2 times the vector u2 plus an times the vector u sub n is equal to the 0 vector. Notice that the only vectors that appear in the sum are vectors from T alone. But now, we knew from the start that a sub 1, a sub 2 through a sub n plus 1 are not all 0. And in this case, number 1, a sub n plus 1 is 0. So that means that the first n, a sub 1, a sub 2 through a sub n, are not all 0. But here we have a non-trivial expression of the 0 vector involving just vectors from T, showing that T must be a linearly dependent set. However, this is a contradiction because the problem assumes that T is a linearly independent set. So case number 1 cannot happen. Let's move to case number 2, where a sub n plus 1 does not equal to 0. In this case, we can move the term involving v over to one side and solve for v. Remember that a sub n plus 1 is a scalar, it's just the number from our field f. And we see now that v can be written as a linear combination of the vectors u1, u2 through u sub n. Hence, the vector v is indeed in the span of T. This completes the proof. Thanks for listening.